I can talk better in this one. All right. So today we're going to be talking about introduction to absolute value function. So how many people in here have heard of an absolute value function? All right, not too bad. Okay. So an absolute value function is basically a function that all of the outcome values, the y values, are going to basically turn and be a reflection of the other side of the graph. And this is over what we call the axis of symmetry. Axis of symmetry. Okay. I'm like out of breath for some reason. Okay. And anybody know what we call this point right here on the graph? What is it called? It's called the vertex. So the vertex on an absolute value function is known as h comma k. Okay, h denotes the x coordinate and y denotes k denotes the y coordinate. And the axis of symmetry is always the equation of the line called x equals h. So it's always x equals whatever that number is. That's the x coordinate.
We did this like in Algebra 1.
You do a little bit.
Yeah, I remember this.
You do, yeah. We're going more in depth today, though. So now we're going to look at the domain. So for every absolute value function, the domain is all real numbers. So I'm going to write it in interval notation, negative infinity to positive infinity. All right, negative infinity to positive infinity. And the range will actually vary based on what absolute value function that we're looking at, because we're looking today specifically at the absolute value parent function. So you've all heard of a parent function before? In case you haven't, a parent function is basically just like the main basic example of any group of function in the function family. So in the function family, we have like quadratic functions, cubic functions, absolute value functions, linear functions, and we call the parent function the most basic form of that function, and then it's been manipulated by shifts and stretches and compresses and things like that. So the range of an absolute value function is typically, it's either going to be this way or it's going to be flipped upside down like an upside down V. In this particular case, the range is from 0 to positive infinity. Now, you may notice I used the square bracket right here. Does everybody understand why I use the square bracket here? It is included because this point is on the graph. It is filled in, so that's why we use a square bracket. If this were an open circle here, I would definitely not use a square bracket, but because it is, I use a square bracket. And now we're going to talk about decreasing and increasing. Before we do that, I want to mention a few important things about that. So, when we're talking about decreasing and increasing intervals, you always use, I don't know why I drew like always S. Always use parentheses, okay? You never use brackets when you're doing decreasing and increasing. So just make sure you know that and are careful of that. So let's talk about what increasing and decreasing is. So I'm going to look at the function on both sides. I'm going to look at this side here, and I'm going to look at this side over here. It's two separate like entities right now, okay? Now, which side, yellow or pink, is the function decreasing? Yellow, right? The function is decreasing on the yellow. And the function is increasing on the pink. So, the function is decreasing from negative infinity all the way until we get to 0. And then from there, at 0, the function changes and it starts increasing, right? From 0 to positive infinity. Now, I will mention, this rule only applies to absolute value functions, okay? So, don't misinterpret me. But, we're talking about decreasing and increasing intervals. You'll notice that they have the same number here and here. Okay, they may be reversed, but they're going to end up having the same number because one function's picking up where the other piece left off. So, lastly, we're going to talk about end behavior. So, what end behavior basically means is what's happening to the function when it leaves your graph. Okay, because remember, these go on for eternity in both directions, right? So, as all my x values go to negative infinity, what happens to my y values? Do they go to positive infinity or negative infinity? They go up or down?
Down to negative, or well, up.
They're going up, right? As x goes negative, y is still going upward,
Okay,
right?
yeah.
So this is positive infinity, but I'll write that out for you in a second. And then over here, as x goes to positive infinity, y also goes to positive infinity. So how you write that mathematically is you say, as x goes to positive infinity, y also goes to positive infinity. As x goes to negative infinity, y goes to positive infinity. Now, specifically for absolute value functions, y is always going to be going the same way on both sides, specifically for absolute value functions. That's because they're either both going up on both sides or they're either going to both be going down. They're never going to be doing different things. And that's because of the symmetry of an absolute value function. So, does anybody have any questions? Yes?
Is y negative infinity on the first one?
No, it's positive. Any other questions? Okay. Wait, did somebody raise their hand? No. Okay. All right, let's move on. So now we're going to talk about transformations of absolute value functions. So every parent function we talk about can always be transformed in some way. And we consider the following types of transformations. So we have horizontal shifts, vertical shift, stretching, and compressing. And then we have vertical reflection, which is basically flipping this way. You have all dealt with types of transformations before in algebra. In Algebra 1, I know because I've taught it before, you deal with linear and you talk about shifting the graph around the axes. And then geometry, you also talk about transformations of coordinates, right? So it's the same situation. I do have a transformations poster that's supposed to help you, but I'm going to put it in a more visible spot because it's kind of over there in the corner. So I'll put that out in a more visible spot for help. So this is what the standard form of an absolute value function looks like. A indicates if it's flipped right side up or upside down. And if A is a greater than 1, it's going to be a stretch. And if A is between 0 and 1, which means if it's a fraction, it's going to be a compression. So we're going to talk about some examples of what that looks like. So we're going to look at example 1. I'll zoom in to make it more visible. Example 1 is an absolute value function, and we're going to look at it in relation to the absolute value standard form. So I always like to write my standard form above it so I can compare and kind of line everything up. So as you can see, this is in standard form. Now the a value, it does have an a value, but it's not as clear here. What do you guys think the a value is? 1. Very good. So it's 1 because the implied coefficient of anything that's not given to you is always 1. Now, if your a value is positive, that means your graph opens upward. Okay? If the a value is positive, that means your graph opens upward. And in this case, my a value is definitely positive. Now, the next thing we're going to look at is h and k, which are the components of my vertex. So, what do you notice about in the formula? What's the sign of h in the formula? Negative. So what does that mean when I look at it in terms of in the equation? What am I going to have to do to the h when I take it out? Good, you guys are smart. I'm going to make it the opposite sign. You probably vaguely remember that from when you deal with quadratics. But yeah, you have to make it the opposite sign, and that goes for any formula you're dealing with. If you ever have a negative in a formula, and the formula has the negative, you have to remove it when you take it out. And then the the k is just as is. And what is the k going to be here? 1. So the vertex is just h comma k, so 2 comma 1. And we're going to graph that. So 2, 1. Looks like it's about here. So that's basically the middle of your graph. Now, it's so important to find the middle of your graph first, and I'll show you why. So what we're going to do now is we're going to make 5 rows here. You can also do 3, but I'm going to show you with 5 to make it more concise. So the reason we pick an odd number of rows is because the middle row, the third row, is always going to be your vertex. So the middle row of your table is always going to be your vertex. So my vertex is 2, comma 1. So this is going to be 2, 1. Now, what is this middle column here? This middle column is for plugging in. Now, we don't have to plug in for the vertex because we already know the y component. This is to help us obtain the y component, which case we already have it. Now, how do you determine the other x values in your table? Well, you're going to go backwards and forwards. So what's 1 less than 2? 1. And 1 less than 1? Good. 1 more than 2?
3.
And 4. So that's why it's so important to determine your vertex before you make your table, because you have to know what section of your graph you're looking at in order to see what the graph's going to look like. So once you obtain these values, you're basically going to take these values and plug them into the equation. So I'm going to replace the x with each of those. And what's 0 plus 2?
Wait, you do plus, not minus?
Oh, my bad.
Okay.
You're right. That was all me. Sorry. Yes, you're right. It ends up being 3 either way, though. And then here, it's going to be 1 minus 2 plus 1. So that's going to be 2. You don't have to do this one because we already have the answer. And that's going to be 2. And this is going to be also 3.
Don't they mirror each other?
Very good, yep. Good observation. You'll notice that these mirror each other. See the mirroring? And if you kept going outward, if you kept picking values less than and greater than, it would just keep mirroring itself, okay? And that's because that's a characteristic of an absolute value function. So now we're going to graph these points. So this is 0, 3, 1, 2. So these are just ordered pairs, okay? And then this is 3, 2. And 4, 3. So as you can see here, you can start to see what your absolute value function looks like, okay? And it should always look like a V or an upside down V, one of the two. And that's that. And then once we've gotten all of that, we're now going to talk about some of its characteristics and key features. So let's talk about the axis of symmetry. So the axis of symmetry is the vertical line that goes right through the middle here. And the equation for that line is always x equals h. In this case, h is 2. So the axis of symmetry is known as x equals 2. Now we're going to look at roots. So does anybody remember what roots look like in terms of a graph? We talked about it a few days ago, the puzzle piece.
The squiggly line and then like...
Yes, you can write them like that, but in a graph, how would I find my roots without doing any algebra, just looking at the graph? It'd be the parts of the graph that cross the x-intercept. Good. So roots are also known as x-intercepts. Remember how we talked about how like roots or x-intercepts and zeros are all the same thing?
Oh, yeah.
So does this graph even cross the x-axis at all?
No.
No, so we don't have any roots here. Now, I do want to come full circle and kind of talk about how that would look algebraically. So you remember a few lessons ago we were doing absolute value functions, and we were like having to do the 2 arrows and do plus and minus and then calculate the zeros, and then we had to plug them back into the function and see if they worked. What this would mean is if you were to algebraically do that math, if you were to plug in 0 for y and do the math here, what would happen is you would get 2 roots that don't actually work.
So like no solution?
No solution, exactly. So that's how that looks in terms of a graph. If there's no solution for an absolute value, what we talked about a few weeks ago, that's what that would look like on the graph. So now we're going to talk about domains. So for any absolute value function, the domain is always all real numbers. And that one doesn't change unless you're binding it, which we're not going to do in this class. You're looking at it from intervals. So now we're going to talk about increase and decrease. So I will highlight one side pink, and I'll highlight one side yellow, so we can get a visual here. So which color is decreasing?
Pink.
Good. And what color is increasing?
Yellow.
Good. So now that we've determined what is what, now we're going to look at where, okay? So it's decreasing from negative infinity, and it stops decreasing at what? What x value? 2. So decreasing and increasing, we always refer to it in terms of the x value. Now, increasing, we increase from 2 to positive infinity. So from here to here. What is up with the rain lately in this class? Was it you guys that it rained really bad the other day? I think it was you guys. Alright, moving on. Let's talk about the range. So in this case, what's the lowest? Oh, go ahead.
So is it bracket, and for this one, the range,
You got it, yeah.
and then 1.
It is going to be a bracket here because this value is included on the range.
Mhm.
So what's the smallest my y value is ever going to be? 1. And the biggest is going to positive infinity. Now, what you're going to notice with your range is your range is always going to involve k. Okay? Either on one side of the interval or the other, depending on how your graph looks, it will always involve k. It with absolute values, not with every function, but with absolute values.
And for the range, your first number will never be like negative infinity or something, or will it?
It will be when your graph's upside down,
Okay.
which
But
we'll
it
get
won't
to.
be positive infinity at that point then.
No, it always goes from left to right.
Okay.
Any other questions? Alright, let's move on to the last bit here, and now we're going to talk about end behavior. So I do want to highlight the end behavior here so that you can kind of get a better visual. So as x goes to negative infinity, that's the pink section of the graph. And as x goes to positive infinity, that's the yellow section of the graph. So as x goes to negative infinity, what happens to the graph? Is it going up this way?
Mhm.
Yeah, so that's positive. And as x goes to positive infinity, is my graph going up or down? Up. So like I said, when we're talking about absolute value functions, these two infinities will always be the same sign. They could both be negative or they could both be positive. And that's because absolute value functions are symmetric. So they're going to be the same on both sides.
So it was upside down, it'd be negative infinity?
Yep, you're already foreshadowing our next examples coming up. Anybody have any questions? Okay. Oh, look at this. It's a negative. All right. What's our a value here?
Negative 1.
Good. And what do you think it's going to open up or down? Good, downward. What's my h here?
1.
Not 1.
Negative 1.
-1. And my k?
Negative 1.
-1. So my vertex is -1, -1. Now you can make a table. Now, I do want to mention, you don't always have to do 5 values. You can if you want. But I'm just going to do 3 here, and I'm going to show you how that still works. But you always want to have an odd number, because you're mirroring itself, right? So I'm just going to do 3 this time, because we don't really need to do all of them. It's just kind of, it's one of those things you're going to like learn as you go through, like if you're going to need to add a value or not. So the middle of your table is always going to be your vertex. And then you're always going to pick values above and below that. So what's 1 less than -1?
-2.
Good. And down here?
0.
Good. Once you have that information, you're going to plug it into the function. So this is one that's kind of a very weird order of operations. So -2 plus 1 is -1. Then we have to make it positive because it's the absolute value, so it's 1. Then I have to make it negative again because the negative outside here. So it's -1 minus 1, which is -2. Now we're going to do 0. So 0 plus 1 is 1. Absolute value of 1 is 1. Make it negative because the negative sign on the outside. -1 minus 1 is -2. Now, lucky for everybody this year, all of your tests are open notes. So you don't have to worry about order of operations stuff because you got a calculator and internet calculators to help you out on this. So don't stress out too much about that. So this is going to be -2, -2, and this is going to be 0, -2. So now we're going to plot this. So -2, -2, -1, -1, and 0, -2. Now if you kept going, it would have plotted here and here and so on with your table. The more table values, the more dots you're going to get to see what your graph looks like. But it's not always necessary. You kind of can see what it looks like without more values. And what do you notice is different about this example than the last?
It's downward and
Good.
and the negative.
Yeah, it's the a value is negative, so now it's flipped over. So my axis of symmetry is x equals -1. Does my graph have any roots?
No.
No roots. Domain is always all real numbers. And now we're going to look at increase, decrease. So yellow, we'll do blue this time. Change it up. Alright, so this is where it's a little different. Where's my graph decreasing now? No.
Yellow.
Here, I always read from, when I'm looking at this, I'm reading from left to right. So pretend you're a person walking here, okay, from left to right. You're going up this way, right? So it's actually increasing over here. And then when I get over here in the blue, it's actually decreasing, right, if you're a little person, right? So it is a little hard to visualize. It took me some time to learn this too. So my graph is actually decreasing on the blue, and it's increasing on the yellow. Okay? Because you're always reading it like this, right, from left to right. So like it's going up for a while and then it comes down. It's like a mountain. So it's decreasing from -2 to positive infinity, right? And it's increasing from negative infinity to -1. Does that make sense? Okay. And then what about my range this time? What do you guys think?
Bracket -1 to -infinity.
You're right, but you're saying it backwards. So it's from negative infinity to -1 because you always have to go from bottom top, left, right. So yeah, it's going to be coming up from negative infinity and it stops at -1. It doesn't go any higher than this. Okay. And lastly, end behavior. Both sides of the graph is going down, so it's negative infinity on both of them. And this will always be the case for any time the a value is negative. You're always going to have two negative infinities. Alright, I'm going to give you guys a 10-minute break. If you want to work on the assignment, you can. If you don't, that's your business. But you got to get your homework in on time. So take a break and we'll come back to the lesson in a little bit.